Hello everyone. Topology is a branch of mathematics that studies properties of geometric spaces that remain unchanged under continuous deformations, such as stretching, shrinking, and bending, as long as we do not tear the space or create or fill any holes. Such properties are called topological invariants. The number and dimension of holes are important examples of topological invariants. Today, we are going to explore homology, a mathematically rigorous method for detecting holes and cavities in a geometric space. Homology is a fundamental idea in algebraic topology, the area of mathematics that translates topological information into algebraic objects such as integers, vector spaces, and groups. Although the subject may look highly abstract, it also plays a central role in topological data analysis. There, persistent homology uses algebraic computations to reveal geometric structures hidden in data. Here's a simple geometric space with a hole, an annulus, which is a region of the plane between two concentric circles. To compute its homology, we first divide it into finitely many basic pieces, place 3 points on the inner circle and label them A, B, and C. Then place 3 points on the outer circle and label them X, Y, and Z. Next, add the 6 connecting edges shown here and choose an orientation for each of the 12 edges. These edges divide the annulus into 6 curved triangular faces, AYZ, BZX, CXY, XBC, YCA, and ZAB. Altogether, we have 6 vertices, or 0 cells, 12 edges, or 1 cells, and 6 faces, or 2 cells. At this stage, the cells are merely geometric objects. There is no natural operation that lets us add one edges to another or subtract one face from another. To introduce algebra, we allow formal sums of cells of the same dimension with integer coefficients. These formal sums are called chains. For example, a zero chain is an element of the free abelian group generated by the vertices. One chains and two chains are defined in exactly the same way. We now define the boundary operator, denoted by partial. It takes a chain of any positive dimension to a chain one dimension lower. The notation is not accidental. This operator is closely related to boundaries in integration into Stokes' theorem, but that is a story for another video. As the name suggests, the boundaries of an oriented edges is its head minus its tail. Thus, the boundary of AB is B minus A, while the boundary of YC is C minus Y. The boundary operator is linear, so the boundaries of a formal sum of edges is the same formal sums of their boundaries. We define the boundary of the two cells in a similar way, using its oriented edges with the appropriate signs. For example, the boundaries of AYZ is AY plus YZ plus ZA. An essential property of the boundary operator is that taking boundary twice always gives 0. In our example, the boundary of the boundaries of AYZ is the boundary of AY plus YZ plus ZA. This is Y minus A plus Z minus Y plus A minus Z, and every term cancels. A one chain whose boundary is 0 is called a one cycle. The boundaries of AYZ is therefore a one cycle. This is also a one boundary because it is already the boundaries of a two chain. Now, consider the one chain AB plus BC plus CA. Its boundary is also 0, so it is another one cycle. However, no matter how we combine the 6 two cells of the annulus, the boundary can never be exactly this inner loop. In other words, this cycle is not a boundary. The situation would be different for a solid disk. The missing central region would then be a two-cell ABC whose boundary is precisely AB plus BC plus CA. This contrast is how homology detects the hole in the annulus. It records cycles that do not arise as boundaries. Formally, the first homology group H1 is a group of 1 cycles divided by the subgroup of 1 boundaries. For the annulus, H1 is isomorphic to the integers, and the loop around the central hole provides a generator. I hope this video has given some insights into homology and what it measures. Thank you for watching, and see you next time.